Hello everybody! The effect I'll be creating in this video originated as a combination of the algorithm used for rendering a 3D tunnel and several applications of so-called fractal Brownian motion, which I explored while working on some of my fractal shaders. And since I most likely didn't explain anything clearly with that introduction, we'll go through everything step by step. Let's get started. And as usual, let's start by creating a new scene in the Godot editor. Then we'll add a color rect to the scene, set the parameters, create a shader material, just the usual stuff. So I'm right-clicking on the scenes folder, create new scene, user interface. Let's call it, for example, magic portal. Sorry, check keyboard. Magic portal. Okay. And right click add child node color rect. And I will set the color to black, open the layout transform properties and set the full HD resolution 1920 by 1080. Okay. And okay, let's make it visible here. Scrolling down to the material section, creating new shader material, click create a new shader, which is called magic shader.gd shader of the canvas item mode, and I'll put it to the shaders folder and create, and click again to open it in the shader editor. Very well. So let's get rid of everything we won't need, only the fragment function remains. I'm deleting vertex and I'm deleting light. Great. Let's start coding. As is common with similar effects, we'll control their properties using a plenty of uniform parameters, which we can then adjust in the inspector. This time, I'll be adding them gradually, so it's clearer what we need each one for. I'll start with the basics: resolution, color, direction, and brightness. So uniform vec2 resolution, and its default value is our full HD resolution, so 1920 and 1080. Okay, this is the first one. We will use it for the aspect ratio recalculation. Then the line color. So we want to color the final effect somehow. Line color and hint source color for the color picker in the inspector, and the initial value, let's put it to a green color. So it's 0, 1, 0, vector 3. Okay, next, the direction of the effect animation. Uniform float direction with a hint range and the initial value, let's set 2.5. And we want the direction in both directions. So let's make the range from -1 to 1 and the step point 0, 1. Very well. And the final one is the brightness. Uniform float brightness with a hint range, and let's set the initial value to 15, and it would be from 0 to 30, and the step again 0.01. Great. So let's move on to the fragment function, where I'll insert the basic code. First, I'll shift the coordinate origin to the center here. So the effect is nicely centered, and then I'll recalculate the aspect ratio to make sure it looks the same regardless of the window dimensions. After all, we do this almost every time. So let's write the usual code in the fragment function. First, vec2 uv is uv minus 0.5, which moves the coordinate origin to the center, and then now the aspect ratio recalculation uvx is multiplied by resolution x divided by resolution y. Okay, what's next? At the beginning of the video, we could notice that the effect looks three-dimensional, as if the portal is pulling its surroundings inwards, or, on the contrary, ejecting its interior outward. That's why this time, two-dimensional UV coordinates won't be enough. We'll also need a third dimension to define the depth of each individual pixel. And for this purpose, let's use the direction parameter, this one, which will control the direction of the ray from the camera to the screen, like this. Vec3 array is Vec3, which is composed of our UV coordinates and the direction value. Crap. Okay, this is correct. Let's continue. As I mentioned at the beginning, this effect combines an algorithm called Fractal Brownian motion with spatial rendering, which you might recognize from tutorials about creating a 3D tunnel. If you've never heard of Fractal Brownian motion, I recommend watching the video where I create a lightning effect. I've included the link to it in the description of this video. For now, it's enough to know that we'll be performing amplitude and frequency calculations over many iterations, which, using certain functions, usually sine and cosine, will give us the desired result. And to keep the code more organized, I'll separate this functionality into its own function, which I'll place before the fragment function. For now, it'll be just a skeleton that doesn't do anything yet. So let's put it here, vector3 fbm, with the input parameter vec3, our array, and let's define the result vector. Vec3 result is vec3 0, and we are simply returning it now. Result. Okay, so now we can add the call to this function at the end of the fragment function. Right here, vec3 result is fbm with the parameter array. Cool. The second thing I mentioned is spatial rendering. Since the FBM function returns a vector 3, we'll use its length in the following formula, which places this value into space and sets its color and brightness. Vector 3 color is vector 3, and now brightness divided by length of our result. Okay, this is the vector, and now we want to multiply that by the line color to color it. Okay, and finally we'll display the resulting color. Color internal variable is vector 4, which composed of our color vector 3 and 1 for the alpha channel. Okay, we have something. It's not very impressive yet, is it? All we have is a bright green color everywhere. It's time to implement the FBM function, which will transform that into the structure we saw at the beginning of this video. We know it was a dynamic effect, so we'll need to set the speed of its movement. So let's add a new uniform parameter and call it speed. Okay, scrolling up to the uniform parameters section and adding uniform float speed with int range and the initial value 1, and let's make the speed from 0 to, for example, 10, and the step again 0.01. Very well, and we'll set a variable that depends on the internal time and the speed value in the FBM function, like this. Float time is time times speed. Great. So as I mentioned, the algorithm works in iterations, so we'll need to set the number of those iterations. In this context, the iterations are called octaves, so that's exactly how we'll name the next uniform parameter. Uniform float octaves, again with the int range and the initial value, let's make it 100. So it's really processed as much as possible. And let's start from 1, and the final value of the range would be 200, and the step can remain as 0.1. Okay, and we'll set up a loop where the actual calculation will take place. For float I from 0 to octaves I++, and we'll do something here, nothing there yet. Alright, now we'll finally display something. In each iteration of this loop, we'll assign the current value of the result vector to a new vector called p, for example. Then we'll perform some operations with this vector p and then add the result back to the result vector. Let's try this simple formula using trigonometric functions. So vec3 p is the current value of result, and the result will be increased by this formula, length of sine, as I mentioned, trigonometric functions, p, and we want it to set it in motion, so plus the time value, then plus cosine, and again p plus time, and finally let's multiply that by our ray direction. Okay, look at that, something has started happening. It's not anything spectacular yet, but we have a moving pattern. And if we change the value of octaves in the inspector, we'll see how it gradually builds up from the individual iterations. Let's find it here. And the octaves, I'll make it lower, and we can see, can you see it? Yeah, this is something really happening there, and it actually looks a bit spatial, or tridimensionals. Alright, so let's get back to the initial value. Anyway, it's not quite right yet, because we are seeing points. It will be more visible if I just decrease the octaves value. We are seeing points instead of moving strands. The problem is that we are using the length of tridimensional vector p, which is vector 3, which is then multiplied again by a three-dimensional vector array, which affects the final rendering. So let's get better results if we use only two components from the vector p. So let's try xy for the sine and xz for the cosine. Dot xy and dot xz. Wait for it. Okay, that looks better. However, it could use more of a sense of depth, which we'll achieve by slightly modifying the z component of the vector p in each iteration. To do that, we'll also add two more uniform parameters. Let's do it here. A uniform float shift with a hint range, and it starts at 1. The hint range would be from 0 to, for example, 10, and again the step is 0.01. And the second one, the uniform float stretch with a hint range, and I'll put it to 10, and the range would be from 1 to 100. And I think we can keep the step as 0.1, the default value. Alright, and let's use them in the loop. So we have the p vector definition, and now p dot z would be increased by time plus I times shift, and it's too big of a value, so let's multiply it by 0.01. So there would be a different shift in each iteration, just slightly shift it. Okay, this is the first one, and now the stretch. So let's do this. Pz would be divided by the stretch value. Okay, it's starting to take shape. However, the lines are too straight, so we'll improve them by applying rotation. For that, we'll first add a rotation function that I've also used in several previous tutorials. It's a standard formula for the 2D rotation. Let's put it here. Mat2 matrix, two-dimensional matrix, rotate with the parameter float a for angle of the rotation, and now float SA is sine of A, float CA is cosine of A, and let's return the final matrix. Return mat2, which is composed of two two-dimensional vectors, so vec2 CASA and vec2 negative SA and CA. Okay, this is it. And let's add this line to the calculation. So let's rotate the xy coordinates and use the z coordinate as the rotation angle. So it would be this way. P dot xy is multiplied by a function rotate with the parameter p dot z. Z. Okay, the effect could still use a bit more randomness. I guess there are some replications and some pattern which repeats over time. So let's try swapping the order of the components of the vector p in the sine function. Instead of xy, I'll use yx. Wait for it. Okay, this looks a little bit better. And yes, I think we are done basically. Now we can adjust the parameters in the inspector and observe how they affect the final effect. So for example, I'll change the direction. Now it's almost, now it's in the opposite direction. And let's get back to the original one. Or I can change brightness, very bright, or we can use a fade out, fade in effect if we control this parameter from the script. Speed, I think it's clear. We can make it very fast, or we can make it to a full stop. Octaves. The more octaves, the more complex the effect is, and we can also get back to the origins to see how it is actually created from the original bright green screen. Or we can play with shift to make it less detailed, or stretch to control the shape of the individual of the final spiral. Very well. One last thing. As usual, we have the effect on a black background, but some might want to use a transparent background. So let's use the usual approach. I'll add a new parameter called alpha threshold. Uniform float alpha threshold with a hint range, and it starts at 0, so it's turned off. 0 I set, and no minus sign here. From 0 to 1 and 0.01 as the step. And let's improve the end of the fragment function here. So first, let's find the average color. Actually, in this case, we could use just a green component for the threshold, but since it's possible to change the line color to anything else, let's make it more universal. Float average color is simply color R plus color G plus color B divided by 3, so it's an arithmetic mean. And this time we won't use just one, but this formula. If AVG is less or equal our alpha threshold, let's make it fully transparent, this point, this pixel, or in other cases, let's make it opaque. Very well, and now when I go to the inspector and change the alpha threshold, we can see how it's becoming the background transparent. And that's it. We can see how it allows us to create interesting variations of the final effect. Thank you very much for watching. This time it wasn't anything groundbreaking, but I still think the final effect looks nice and could be useful to someone. Of course, we could add more uniform parameters to control things like the direction and the speed of rotation or color changes in different layers, but I'm sure everyone can experiment with that on their own. So, take care, good luck with your projects, and I'll see you in the next video.